This example is one that Greg came up, Professor Nellis came up with, but the idea is that you have, let's say, a tube inside another tube. So in that inner tube in there, we have, say, liquid nitrogen. Right? We're trying to transport liquid nitrogen. We want to keep it cold. And so you have this radiation shield around it, and you evacuate the space between these two cylinders. So in here, this area inside this annulus is actually evacuated. So there's no conduction, there's no convection happening in there. It's only a radiation problem. It's relatively long, but we do have the possibility of the end caps of this providing radiation to the different surfaces. So what we want to do is go through, kind of take inventory of what we have here, but we want to calculate the rates of heat transfer to the surfaces, understand what are the view factors involved, and kind of go through the process. So the first thing to notice is we have 1, 2, 3, 4 surfaces. So we have a 4-surface problem, so it's not that helpful for us to write out a resistance network. We want to go through and actually do the n-surface type problem. And then we're going to need the area. So we need area for surface 1, 2, 3, and 4. So it should be area 4 here. Okay, so we have these different areas. Obviously, the end cap areas are equal to each other. So what is the first thing we're going to need to do? We need to figure out what's the view factor table look like for each of them. So we need to know view factor 1 to every other surface, and so on, right? We need to compute the view factors. So let's go through that process. That's like 80% of what we have to do in this problem. Let's start with surface 1 here. So surface 1 is this inner tube here. Let's figure out what are the view factors from 1 to the other surfaces. So let's start with F1 to 1. We have this cylinder. Anybody could just tell me what F1 was, right? 0. So F11 can't see itself, so it's 0. That cylinder, when it emits radiation, it has to go away from it, so that's 0. Let's see. So we could also do, let's see, F12. So what's the first thing we know about F12? So that's going to be what? F12 is from this surface to this surface to an end cap. So first of all, we know F12 is equal to F13 by what we call symmetry, right? They're symmetric. It's the same thing as happening on both sides. So we know F12 is equal to F13, but could we, from inspection, decide what that is? Probably not. Right? So, probably what we need to do is go to a library for this. So we could go to ease. I've already started this problem. We've entered in and calculated the areas. We have our view factor F11. So what I want to do now is use a library. So here I found that this F3D6 actually is a good match. We can look at this F3D6. Right here we have a cylinder to some concentric ring cap, basically. We're going from A1 to A2. We're always from 1 to 2. So this is the right one to work. So we just pull this out. We have to make note, okay, R1, R2, and L are parameters we need. So we pull that out and we plug those in here, R1, R2, and L. Okay, so that's going to be from, what was it, F3D_6. So we'll get those, we'll look those up. Then we're left with F14. So who knows how we can calculate F14? Yes, exactly. So F14, if all those view factors have to add up to 1, we just can say, okay, this is 1 minus F11, F11 minus F12 minus F13. So I can go through and enter those in, and now I should have the first row in my little matrix, if we go back here and solve this, I should have in the arrays table, the first row in my matrix is now completed, right? So the same process, you just keep going through. So now we have, let's look back. So now we'd have to do, for surface 2, kind of going short on time, but for surface 2, I'm going to, or sorry, let's actually do it this way. So I'm going to go to surface 4 next. And so surface 4, I do F41 equals something. Well, I just calculated F14, right? So I can use reciprocity there. That's going to look like A1 over A4 times F14, just solving for that view factor. So I, for free, have gotten that one without having to do anything else, right? I can do that. F44, there, it's a cylinder to itself. That's not obvious. I have to use a library for that. Right? So you just keep going through this process. And since we're short on time, I'll kind of skip to the answer here. So you can see where you just go through this process. And to me, it kind of reminds me, like, you get enough information, then you can fill in the remaining thing with the enclosure rule. So it kind of is the same for your parents, or maybe you have done like Sudoku, right? It's kind of like a Sudoku. It's a little puzzle. You're trying to fill in the little gaps and use information from one part to fill in the other part. And you ultimately end up with something like this, where you have now a full completed view factor table for every possible view factor. And then you come back and you write your energy balance on each surface. So now I'm going to use this duplicate loop to write for every surface, I equals 1 to 4, this balance, right? And this is now the balance. I'm summing up the view factor times the temperature difference for all the surfaces. So I'm doing that for every surface. And then I can come back and it will tell me, sorry, you don't actually have enough. It's thinking. It should tell me you don't have enough information. So we need to add in our 4 more boundary conditions. We have specified temperatures, specified heat flux, and from that, then we should be able to solve. Okay? Sorry, I kept you 2 extra minutes. Thanks, everyone.